membrane potential wasn't at minus 70 millivolts? What if it was at minus 90 millivolts? Are we closer to threshold? Are we at the same distance from threshold? Or are we further from threshold? This really should be a rhetorical question, but what's your answer? We're further from threshold. Do you think it's going to be, we'll be able to use the same strength of stimulus against the threshold? Do you think we'll need a smaller stimulus or a greater stimulus? Greater stimulus, that's exactly right. And so, by manipulating where the resting membrane potential is, we can make the cell less excitable or we can make it more excitable. Now, if you've been listening to me, and I know you guys have, all throughout the semester, beginning of the first night, I told you that if you, as a healthcare provider, if you're a nurse, a PA, and you're not looking at the resting levels of potassium, that's malpractice. If you've got a patient who's having arrhythmias, you're in deep doo-doo if they go into fatal arrhythmia. If you have a high concentration of potassium in the plasma or outside the cell, your resting membrane potential is going to be closer to threshold. Is it going to be easier to excite cells or more difficult to excite? The answer should be really obvious. It's going to be much easier to excite cells. And in individuals who have arrhythmias, their cells are already irritated. They're already excitable. And with elevations in potassium, you can just push that person right over the edge where they go into a fatal rhythm. And when I talk about fatal rhythm, I'm not talking about the atrium. All of you guys know that the heart's a four-chambered organ. There's two atria. Those are assist pumps. You can live without them for the most part. You cannot live without either ventricle, but most importantly, the left ventricle. The left ventricle's job is to ensure that every cell in your body gets adequate amounts of oxygen. And if you go into VFib, then the pumping action of the left ventricle goes to that right there. That means you're on the clock. You got 5 minutes to resolve that problem. If not, now we're starting to get into an arena where we're talking about injury to the brain. Serious injury to the brain. So what you're going to do in the next part is you're going to vary the concentrations of potassium, but I need to make sure you see how that's going to be achieved. So sadly, in this experiment, there's nowhere in here, whoops, always helps if I have the screen down. It would have been nice if they had in the control panel an area where you could change the concentration of potassium. But no such luck. But, the way in which you're going to manipulate the effect of changing the concentration of potassium is by altering the equilibrium potential. So if you change the equilibrium potential, if you increase the concentration of potassium, that's going to change the equilibrium potential. If you lower it, that's going to change the equilibrium potential. You're going to simply put in the new equilibrium potential for each of the conditions in the table. And those conditions are as follows. So here we go. Here's the concentration of potassium outside the cell. And that's what we're manipulating. We can't manipulate the concentration of potassium inside the cell. It's outside the cell that the changes are occurring. So here's concentration of potassium, subscript O, meaning outside the cell. What are you going to put the inside at? What's the inside value going to be? Help me out. Can't hear you guys. Say at 140, right? That's what it's going to be. So what we're doing is we're simply changing the concentration of potassium outside, and you're going to stimulate the cell using these different amplitudes. So here's our baseline right here. 4 millimolar outside, 140 millimolar inside. That's this first data set. Then you're going to come along and you're going to calculate the equilibrium potential for potassium when the concentration is 2 millimolar outside. And then that's where you're going to use that equilibrium potential with that new condition. Oops. And you're going to change the value simply here. And you're just going to keep playing that game at all the different concentrations. You guys ready to get rock and roll? All right, let's do it. I'll break out the computers here. You guys come on up. Look at the number on your table. You guys are one. No, yeah. No, I think. Are you two?
Real one.
Okay. So if you look where that little Ethernet port is, that tells you your table number. You guys, for instance,